Kubernetes administration from 0 to hero, junior level. Agenda is interaction, accessing the Kubernetes API, Kubernetes workload. Fourth one is accessing applications, and fifth one is volumes and persist storage. Introduction: cloud computing in general, cloud native computing, Kubernetes overview, Kubernetes architecture. Cloud computing in general, a model for enabling ambiguous network access to a shared pool of configuration computing resources. Resources is nothing but compute, storage, network, apps as services. So resources are allocated on demand. Scaling and removal also happen rapidly. Seconds in a minute. Multi-tenancy. In the sense, shared resources among thousands of users and resources quotas. Cloud computing is a cost-effective in IT. Pay-as-you-go model. Pay per hour, gigabytes instead of flat rates. Maximized effectiveness of the shared resources. Maybe over provisioning. Lower barrier to entry. Nice for startups. So focus on your businesses instead of your infrastructure. This is the benefit of cloud computing. Cloud native computing, in the sense, a new computing paradigm that is optimized for modern distributed system environments, capable of scaling to tens of thousands of self-healing multi-tenant nodes. Main properties of cloud native computing. First one is container package. Containers represents an isolated units of application deployment. Dynamic managed, actively scheduled and actively managed by a control orchestration process. And also microservice oriented, loosely coupled with dependencies explicitly described. Is nothing but through service and outputs endpoints. Application containers. So application containers are OS level virtualization. OS partitioning is nothing but virtual OS versus virtual hardware. So it allows us to run multiple isolated user space applications instances in parallel, and also instances will have application code, required libraries, runtime. Self-sufficient application containers are self-sufficient. No extra dependencies, and also it is portable, lightweight, immutable images. So this is the hardware and operating system, libraries and application. These are nothing but containers. Container orchestration. Container orchestration tools that are providing an enterprise level framework for integrating and managing containers at scale. And also it aims to simplify container management. A framework for defining initial container deployment, availability, scaling, networks. A container orchestration tools are Docker Swarm, Mesosphere, Marathon, Kubernetes. These are the managing container orchestration managing tools. Kubernetes. So Kubernetes, ancient Greek word for helmsman or pilot of the ship. The meaning of the Kubernetes is pilot of the ship. So initially developed by Google. Kubernetes is initially developed by Google. So it has its own origin in Box Cluster Manager. Kubernetes is an open source system for automating deployment, scaling, and management of containers applications. Places containers on nodes, recovers from failures, basic monitoring, logging, health checking, enables containers to find each other. Kubernetes concepts. Kubernetes Master. The Kubernetes concepts are three types: Kubernetes Master, Kubernetes Nodes, Kubernetes Objects, Kubernetes Spaces, Labels, and label sectors and annotations. So, in the Kubernetes Master, maintain the desired state for the clusters. Kubernetes Nodes runs the application. So, Kubernetes Objects abstracts that represent the state of the cluster, a record of the intent, a desired state of the cluster. Objects have specification describes its desired state describes the actual state updated by Kubernetes. Name client provided, unique for the kind in a space name, can be reused. Namespaces are nothing but virtual clusters provided a scope for names. In Kubernetes concept, labels are key value pairs attached to objects. Label sector is the core grouping primitive. Annotations attached arbitrary non-identifying metadata to objects. Kubernetes objects categories, workloads. So these are the objects categories in Kubernetes: workload, discovery, LB, and config and storage and metadata cluster. These are the objects categories of the Kubernetes. So in workload in the sense workload is used to manage and run the containers, pod replication controller deployments. Discover and LB sticks is used for workload together into an external accessible load balanced service ingress. And config and storage objects we can use to inject initialization data into applications and to pass data that is external to the containers. Volume secrets and metadata objects used to configure the behavior of the other resources within a cluster. It is nothing but limit range. Cluster objects responsible for defining the configuration of the cluster itself. Namespaces binding. Kubernetes architecture, Kubernetes Master, Kubernetes Nodes. So this is the Kubernetes architecture. So we have Kubernetes Master and Kubernetes Nodes, and there is a DevOps guy. In Kubernetes Master, we have etcd, API server, and scheduler and controller manager. In Kubernetes Node, we have a kubelet and Proxy container. In container engine, we have a pods. So this is the Kubernetes architecture. In Kubernetes Master, we can describe provides the clusters control plane. Kube API server expose the Kubernetes API. The front end for the Kubernetes control plane designs to scale horizontal. etcd in the sense is the backing store of the Kubernetes distributed key value store, and also kube control manager in Kubernetes Master. Background threads that handle routine tasks: node controller, replication controller, endpoint controller, service accounts, and token controller. Kube scheduler assigns nodes to the newly created pods. So again I wanted to explain about Kubernetes Master architecture. It has a etcd, and it has API server, and it has a scheduler, and it has control manager. Kubernetes node kubelet, the primary node agent. It watches for pods that have been assigned to its node. So in Kubernetes nodes, it has kubelet proxy, proxy, container engine. In container engine, we have a pods. Kubelet, the primary node agent. Kubelet is a primary node agent. It watches for pods that have been assigned to its nodes. Mounts the pods. It requires mounts to pods required volumes, and download the pod secrets and run the pod containers. Periodically executes any requested containers, leaves the liveness props, and reports the status of the pod. Reports the status of the node. Yeah, these are the functions a kubelet will do in Kubernetes node. And kube proxy. Kube proxy, in the sense, it enables the Kubernetes service abstraction by maintaining network rules on the host and performing connection forwarding. And also we have a container engine. It is used to run the containers, and Docker by default, RKT optionally. And container runtime interface paves the way to alternative runtimes. So in Kubernetes node we have, once again I wanted to tell you, in Kubernetes node we have kubelet, kube proxy, container engine. In container engine, what's exercise 1, the lab environment, understanding the classroom environment using kubectl. So here there are these are the instances which we have using for installing Kubernetes. Kubernetes Master, worker node 1, worker node 2, worker node 3. So this is the IP 10 dot management peer management IP 10.10.10.0./24. So what will happen here? Accessing the Kubernetes APIs. So there are ways to access the API, and controlling the access to the API, and authentication, authorization, role based access control. These are the accessing the Kubernetes API. Accessing the Kubernetes cluster, kubectl, the command line tool for deploying and managing applications on Kubernetes. Inspect cluster resources, creating, deleting, update components and configuration file, /.kube/config information for finding and accessing a cluster. Base auto completion dashboard, web based user interface add-on. It manages the applications, and it manages the cluster itself. Direct access to the API, HTTP REST access. These are the accessing the Kubernetes cluster. You can access it by kubectl, the command line tool for deploying and managing applications on Kubernetes. So what will happen? It will inspect cluster resources, and it will create, delete and update components, and configuration file. In the configuration file, so controlling access to the API. A request for the API will pass several stages before reaching it. So this is the controlling access to the API. So request, authentication, authorization, admission control, and resources. Authentication. So from the authentication, authentication in the sense, ensure that the user it is who it pretends to be. Kubernetes has two categories of users: server account managed by Kubernetes, and normal users managed by an independent services. API request can be API request can be treated as anonymous ones if are not tied to a user or service account. Kubernetes uses client certificates, whereas bearer tokens, and an authenticating proxy or HTTP basic authentication to authenticate API request through the authentication plugins. So these are the controlling access to the API. Authorization in the sense, after the user authentication steps, the request will have to pass the authorization step. All parts of an API request must be allowed by some policy. So this is nothing but permissions are denied by the default. Authorization modules, node, ABAC, attribute based access control. ABAC in the sense, attribute based access control. RBAC means role based access control. And also webhook, we can This is the authorization modules for Kubernetes. Role based access control is nothing but RBAC. RBAC allows fines grained rules for accessing the cluster, allows dynamic configuration of policies through the Kubernetes API. It allows dynamic configuration of the policies through the Kubernetes API. It uses the rbac.authorization.kubernetes.io API group, and it defines roles and role binding in order to assigning permissions to subnets. And these permissions can be set cluster wide. So in cluster wide, it can be used for cluster scope resources, non-resources, endpoints, and namespace resources across all namespaces within the namespace, and also for one single resource. These are the permissions can be set for role-based access control. Subjects can be users, groups, and service accounts. Roles and cluster roles. RBAC roles contains the rules that represents the permissions. Permissions are purely addictive. A role can be defined within a namespace or cluster wide. Cluster role. This is the role we have to define for in the cluster roles. So kind is a role and API version is rbac.authorization.k8s.io /v1 beta 1. Metadata namespace is the default and name is a pod reader. Roles are is nothing but API groups. Groups we can give anything. Resources, pods, and webs is a get watch list. Okay, cluster roles are not namespaced. Cluster roles are not namespaced. Role binding. Role binding grants the permissions defined in a role to a subject. Permissions can be granted within the namespace with a role binding or cluster wide with a cluster role binding. A role binding can be used a cluster role. The rules will apply to the namespace of the binding. So role bindings can be we can use kind is a role binding and API version is a rbac.authorization.k8s.io v1 beta, and metadata namespace is a read pod, and namespaces development, it is a development namespace. So subjects are kind, user name is a dev, API groups rbac.authorization.k8s.io role ref kind cluster role names is equal to cluster pod reader, API groups is equal to rbac authorization k8.io. Exercise 2 RBAC. Use RBAC to control access to the API. Exercise 3 Kubernetes workloads. Pod, replication controls, deployments, replica sets, jobs and cron jobs, and daemon sets. The pod. Pod in the sense the smallest deployable object in the Kubernetes object model. It runs a single instance of an application. Contains one or more application containers, storage resources, a unique IP address. Options about how the containers should run. Containers in one pod are sharing the network namespaces and storage resources. A pod is a scheduler on a node and remains there until terminated or vacated. Pods do not shelf yield by themselves controlled. This is the diagram for pod. Network namespaces, you can use pods, and containers are deployed in pod. Container 1, container 2, and it will attach to the volume. The containers will attach to the volume. The pod, that's what cont. Pod life cycle. Pod has a life cycle, so it has pending, running, succeeded, and failed. This is the life cycle of pod. So pending pod has been accepted by the Kubernetes system, but one or more of the containers images has not been created. This is the pending life cycle of pod. Running running in the sense it has been bound to the node. All of the containers have been created. At least one container is still running or starting or restarting. Succeeded. All containers have terminated in success and will not be restarted. Is nothing but succeeded. Failed. In fail, all containers have terminated. At least one has terminated in failure. Unknown. The state of the pod could not be obtained. So props props of the props of the pod performed by the kubelet on the container using an handler. Prop types. What is testing? Readiness prop, liveness prop. Handler types. How is testing? Exe action, TCP socket actions, HTTP get action, prop result, success, failure, unknown. Restart policy. Restart policy. Restart a pod based on the liveness test results. Restart policy is always on play. Restart policy is nothing but always on failure and never. Pods are restarting on the same node. Only controllers can schedule a new pod on a different node. So this is the pod. Pods are restarting on the same node. Only controllers can be scheduled a new pod on the different node. Our first pod, describing a pod using YAML file. We have to write the YAML file for describing a pod. So our first pod is we have to start with API version v1. This is the version of the pod, and kind is a pod. This is the kind in our YAML file. Metadata name is equal to busybox. So specifications is restarting policy on failure, and containers name busybox, and image is a busybox. We are using busybox image here, and command is called sleep. Arguments is 100. After 100 seconds it will sleep automatically when busybox operations on pods. Create the pod using the kubectl command. Kubectl create -f pod1.yaml. Check the pod status. Kubectl get pod busybox. Kubectl get pod -f watch. Get information about the pod. We are using command as kubectl describe pod busybox, and also kubectl get pod busybox -o yaml. Check the logs of the pod. We can use the command as kubectl logs busybox. Execute a command inside the pod. Kubectl exe -ti busybox sh. Delete the pod. Kubectl delete pod busybox. Replica set. The replica set controller simply ensures that the desired number of pods matches it. Label sector exist and are optional. If the labels of the pod are modified and they do not match the label sector, then a new pod is spawned. The old one stays there. So the replica set provides a declarative definition of what a pod should be and how many of it should be running at a time. So this is the replica set YAML file, rs1.yaml file. We are starting with the API version. API version is a apps v1, and kind is a replica set. Metadata in the metadata we are going to give name, specifications, and template. So here name is nginx. We are using nginx image here for replica sets. Replica sets is equal 3. So three how many three in the replicas three in the sense how many of it should be running on at a time. Select match label in the under match label app nginx template metadata name nginx labels app nginx specifications containers name nginx image is equal to nginx. Working with replica set, create a replica set kubectl create -f rs1.aml. Check the status of the replica set. So we can use the command as kubectl get rs -watch, and also we can use kubectl describes rs nginx. So because we are using nginx image in replica sets, change the number of the replications. Kubectl scales rs nginx replicas is equal to 3. Delete the replica set. We are using command as kubectl delete rs nginx. Deployments. A deployment provides declarative updates for the pods and replica sets. Deployment creates replica sets, which creates the pods. Updating a deployment creates a new replica set and updates the revision of the deployment. And also during the update pods from the initial rs replica sets are scaled down, while pods from the new rs are scaled up. Roll back to the earlier revision. We will update the revision of the deployment. The record flag of the kubectl allows us to record a current command in the annotation of the resources being created or updated. Strategy: how to replace the old pods. We can use two methods. Rolling update is equal to max unavailable or max search or recreate. Working with deployments. Creating a deployment, we can use the command as kubectl run ghost -image equals to ghost -record. And also for creating deployments we can use the command as kubectl create -f dip1.aml -record. So this is the dip1.aml file. So it will start with the API version and also kind, name of the image and specifications, and metadata, template, replicas, how many replicas are running in the deployment, and also specifications, containers, name, image, port of the container we have to give while working with the deployments. Deployment nginx replicas is equal to 3 replica set. This is the diagram for while working with deployments. So these are the containers, these are the pods inside the replica set. So inside the replicas, inside the deployment of nginx, we have a replica set. Inside replica set we have a pods. nginx ay ftks is equal to this is the IP address of 10.44.0.78. So another pod, another container is belongs to IP address 10.0.0, and also same as third one. Working with deployments cont. Check the status. We are using command as kubectl get deployment nginx -watch, and also one more command is additional command is also there. We are using kubectl get deployment nginx -aml, and one more command is also there. Kubectl describes deployment nginx. Scale a deployment. Kubectl scale deployment nginx -replicas is equal to 4. So this is the diagram of working with deployments. Kubectl scales deployment nginx -replicas is equal to 4. Working with deployment. Update the deployment. Kubectl set image deployment / we are using nginx image. Nginx the name of the nginx is equal to nginx, and version of the nginx is equal to 1.7.9, and hyphen all is equal to true. And also update the deployment. We are going to use a command as kubectl edit deployment nginx. Check the status of the rollout. So kubectl rollout status deployment nginx. And also we can use kubectl rollout history deployment nginx. Under a rollout, kubectl rollout under deployment / nginx hyphen 2 revision is equal to 2. Pause and resume a deployment allows multiple changes. Kubectl rollback pause deployment / nginx. We can use also for using pause and resume the deployment. Kubectl rollout resumes deployment / nginx. In Kubernetes jobs, cron jobs. So a job creates a one or more pods and ensure that a specific number of them are successfully terminated. Job can be used to reliably run a pod to completion the specific number of times. Completion. Job can run multiple pods in a parallel. So jobs can run multiple pods in a parallel. Specification parallelism. It is called as specification parallelism. And pods in a job can only use never or on failure as their restart policy. And also it is up to the users to delete old jobs after noting their status, and deleting a job will delete the related pods. And also if the pods are failing, the jobs will create new pods forever. The dot spec dot active deadline seconds will limit the time for which a job will create a new pod. Cron job can create a job once and repeatedly at this specific time. Dot specific dot job template will specify the jobs to be created. Concurrency policy. It has allow, forbid, and replace. Jobs example. It will start with the API version, batch v1, and it will and also kind, metadata, completion, and parallelism, and template metadata. Under the metadata we have to give container name, container image, and commands of the job, and also restart policy. Cron job example. It is also start with API version and kind, metadata. Under metadata we have to give the job name and specifications. What are the jobs you are going to do, and what are the schedules, what are the times, and specifications, and container names, and image which you are going to use in this job, and command and restart policy. If it is a restart policy, you can use that. Daemon sets. A daemon sets ensure that all other some nodes run a copy of the pod. When nodes are added to the cluster, pods are added to them. When nodes are removed from the cluster, these pods are garbage collected. So daemon sets to run pods only on the same node. We have to give spec dot template dot spec dot node selector. So this is the like a pod started on the nodes that matches the node selector. And dot spec dot template dot spec dot affinity. Pods are created on nodes that matches the node affinity. If node labels are changed, the daemon sets will be promptly adopted. Deleting and daemon set will delete the pods except hyphen cascade is equal to false. Update strategy on delete. New pods will be created when the old ones are manually deleted. And also rolling update. After you update the daemon set template, once pods will be killed, you can rolling update. Exercise. This is the exercise in Kubernetes workload. So task is working with pods and working with deployments. So accessing the application services. Service, an abstraction which defines a logical set of pods and a policy by which to access them. The service maps an incoming ports to the target port. The pods targeted are defined by the selector. Endpoints, we can have services without selector. No endpoints objects is created automatically. IP tables proxies depends on working readiness. Props services discovery environments variables are created when the pods is created. Requires over ordering, the service should be defining first. DNS optional clusters add, no order is required. These are the services in Kubernetes. Service type cluster IP expose the service on the cluster internal IP only reachable from within the cluster. Default node port expose the service on each node's IP and the static port. The service will be reachable from outside the cluster using node IP node port. Load balancer expose the service externally using a cloud provider's load balancer. External name maps the services to the content of the external name field by returning a cname records with its value. These are the services types. Working with services expose the ports of the deployment RC. We can use the command as kubectl expose deployments and deployment and nginx hyphen port is equal to 80 hyphen type is equal to node port. Create a services from file. We can use the first kind and after that we have to use API version and metadata. Under the metadata we have to give the name of the file and specifications and app ports, what is the target port and what is the protocol we are going to use. So these are the services files. These all are parameters in services file. Mm, uh, After that for creating the services we are going to use we have to fire the command as kubectl create -f svs1.ml. Working with services get service information kubectl get service and kubectl describes svs. Check service discovery kubectl exe-ti busybox environment kubectl exe-ti busybox ns lookups nginx. Check the IP tables rules on the nodes. So we have to use command as IP tables -t nat -l -n. And also we can use the command as IP tables capital L and capital N small n. These are the exercises in services. We have to work with services and next objective persistent storage in Kubernetes. These are the volumes, persistent volumes and volume claims and secret config map. Volumes by default the container file system is emperor recreated each time when the container starts. A clean state each time can be a problem for trivial applications. A pod can have multiple containers that are sharing files. A volume in the simplest form is just a directory which is accessible to the containers in a pod. The type of volume determines the backend of the directory. The pod definition specifies what volumes are provided, the specific volume fields, and where are these mounted in the container. The specific containers volumes field. The containers are independently specifying where to mount each volume. The same volumes can be mounted on different paths in different containers. So this is the volume example. First we have to give API version and after that we have to give kind metadata. Under metadata what is the file name we are going to use, name, test PD, and after that specifications, containers, image, name, volume and mount path. These are the volumes. name and empty directory. Volume types. Kubernetes supports several volume types. Empty directory, initial empty and deleted when the pod is deleted, survives crashes. Host path, mount a directory from the host into the pod. The content is host specific. Pods with identically specs can be behave differently on the different nodes. GCE persistent disk mounts at a Google Compute Engine. GCE persist disk in the pod. Content preserved on the pod delete. Prepopulated data hands up. AWS Elastic Block Storage mounts an Amazon Web Services EBS volume into the pod's content preserved. NFS allows an existing NFS shares to be mounted into the pod. Allows multiple writers. The server should be configured. Content is preserved. ISCSI single writer can be mounted read only by multiple pods. Clusters multiple writers. RBD single writer can be mounted read only by multiple pods. CPS multiple writers secret. Persistent volume claim. Persistent volume PV is nothing but a cluster of resources that hides the details of the storage implementation from the pod. It can be a different types: host path, NFS, ISCSI, RBD, and plugins are independent from the pods that are using them. Persistent volume claim (PVC), a request for storage by the pod. PVCs will consume PV resources. PVC can request size, access mode, storage class. As storage class describes the classes of the storages. Classes can map to quality of service level. Backup policies allows for dynamic provisioning of PVC. The pod definition will use the PVC for defining the volumes consumed by the containers. Dynamic provisioning is possible using the storage class definition. The storage class will contain the provisioners and parameter field. Persistent volume examples. First, we define the PV. Persistent volume API. We have to give first API version and kind. Metadata, under metadata we have to give name and specifications. Storage, we have to give capacity and storage. Access modes, read what are the accesses, we have to read write once. And persist volume reclaiming policy, recycle. And storage class name is equal to slow. NFS, the NFS path is equal to /tmp server IP address. Persistent volume examples, we define the PVC, the claim. We have to give kind, API version and metadata and name, specification, accessible modes and resources, request, storage and storage class name. Persistent volume examples, the pod consumers, we have to give kind, API version, metadata, name, my pod and specifications. Container, the container name and image which we are going for the creating the container. And volume mounts, mount path is /var www.html. The name of the pod is equal to my pd and volumes is equal to my pd volume. Persistent volume claim and claim names is equal to my name. Secret objects are intended to hold sensitive information such as passwords, safer than putting sensitive information into pod definitions or Docker images. Secrets can be used by the pods as follows in a volume or injected by the kubelet. Secrets can be created from files or directly specifying them. You can use the command as kubectl create secret generic mysql --- from -literal is equal to password and my password. Checking the secrets. Kubectl get secrets. MySQL, we are going we can use the command as kubectl get secret mysql -0 ml. Using secrets as a environmental variables, you can use the environmental variables like specific containers, container image, and name. And environments is equal to name, mysql root, password. Value from secret, the value of the password is equal to secret key reference and name of the file is equal to mysql, and key is equal to password. Using secrets as a volume, specific container, image, busybox, command, sleep 360, volumes, mounts, and mount path, and mysql passwords and name mysql. This is the secret volumes to keep your passwords. Config map. Config map objects are intended for passing information that tends to be stored in a single config file. Can store key value files or plain configuration files. We are going to use command as kubectl create config map special config hyphen from literal is equal to special dot how is equal to vary. And also you can use command as kubectl create config map my map hyphen from hyphen file and is equal to app dot config. Check the value stores in a map. Kubectl get config map my map hyphen ml. Passing the values of the pod. You can use environmental variables part of the pod definition. So here is the environmental variables, and as volumes you can use the volumes name and name of the configuration and configure maps. This is the exercise storage in a Kubernetes. Use the volumes in containers.